Yeah, like this kind of fun. You just have to do that. This is negative and this is positive. And you just like make it and you get like one. Oh. That's like a fancy way of doing it. If I remember.
All right, Daniel's not here yet? No?
He loves me at average juggling.
All right, folks, let's get started. First of all, is everybody ready for the big calculus test today?
Yep.
Yeah. I'm just kidding. I'm taking a calculus test today. It's at 3 o'clock. I'm pretty excited. You guys, you don't have to take a test today, but I get to.
Are you ready?
Relatively. I'll keep studying until the minute I take it. But, all right, so how do you read the notation of an integral? If you have an integral, such as this one right here, and by the way, this is what we get to finally start doing today. If we have an integral for, say, 3 to 4 of x squared dx, then how do we read that? What are we finding here? Yeah, we're looking for the area of a parabola. So here's my parabola, and then here's 1, 2, 3, 4. And we're looking for what, Mario? Yeah, just the area between 3 and 4. Now, you might look at that and say, who cares about that? Like, why would you ever want to know just that one little slice of area? But you never know. You might want to. Especially if this, say, represents your velocity, then remember previously how we talked about distance, velocity, and acceleration? So remember, if your function is distance and your derivative is velocity and your second derivative is acceleration, and so now watch very closely here. If you go this way, you're doing the derivative. If you go this way, you're doing the derivative. But what happens if you go this way? You're doing the integral. And therefore, if, okay, that didn't look too good. So if this function right here represents my velocity, and I take the integral of it, what is that going to tell me? If I do the integral of velocity, what does it tell me? Distance. Yeah, distance. So if that happens to be my velocity, then I'm saying here between 3 and 4 seconds, how far did I go? So there is a very good reason why you might be interested in an area like that. As an area, it looks uninteresting, like a weird shape. But if you interpret this as a velocity and the integral velocity is distance, then you actually found something important, which is how far a speeding object went. Okay, so that's how you read an integral. We're looking between 3 and 4 of that function. We're finding the area trapped between the function and the x-axis. How do you take the antiderivative of a power function? So let's do this one in 2 parts. First of all, how do you do a derivative of a power function? So what are those steps? Ashley, welcome back. Go ahead and tell us. How do you do the derivative? Yeah, very good. And so what are those 2 steps? If I wrote them down in order, the first thing you do? Yeah, you multiply by the power. And then the second thing you do is subtract 1. Okay, it's important that we write those steps down in order so that now we can turn around and do the antiderivative. So the antiderivative, do I just do the opposite of these?
Yeah.
And in the reverse order. So if I want to do the antiderivative, I would have to add 1 to the exponent. And then, what? Divide by the result, whatever that result happens to be. So here's my antiderivative of, let's say we did 5x to the 3rd. So how would I do that antiderivative? Anna, welcome back. Go ahead. How would I do it?
You add the exponent.
You're going to add 1 to the exponent, so I'm going to add 1 to make it 4, and then?
Divide the result.
And then divide by that 4. Yeah. And keep in mind, folks, if there's no coefficient, let's say that there's no coefficient right there. Let me go ahead and make myself some more space. Let's say I want to do the antiderivative of x to the 6th. So, Wendy, how would I do the antiderivative of x to the 6th? What's the first thing I do? Add 1. And then I have to divide by that. What do I put right here to help me do that?
A 1.
Yeah, a 1. Because if there's no coefficient, it's really a 1. And if you put that there and put a fraction line, that helps you to have a spot to put the 7. So that's very helpful to put the coefficient there if there isn't one. Here's a tricky one. What if you already have 2/3 x to the 10th? How do you do that antiderivative? What do you think, Adam? What's the first thing you do?
Oh, you add.
Add 1 to the exponent, and then how do you divide 2/3 by 11? What's the quick and easy way for us to know how to do 2/3 divided by 11? Well, that's true. You're going to multiply by the reciprocal. So that's really 2/3 times 1/11, which is 2/33. So what's the fast way we can think about that, folks? If you want to divide by 11, what's another way of writing that? Dividing by 11 is really 1/11. So you could put that 1/11 right next to the 2/3, and then you would see that it's 2/33 x to the 11th. Okay, so this is how you do the antiderivative of the power rule. Okay, any questions, thoughts? All right. What is the fundamental theorem of calculus? Well, we had a couple different formulas they gave us last time. The fundamental theorem of calculus, where was it? Do you have your 3.2 packet out? What does it say? The fundamental theorem of calculus is how to do an integral. So it says the integral from a to b of f of x dx. And actually what it says is that that is the derivative function. The function that's in there is technically the derivative of some function. So that the first thing you do is do the antiderivative, and the antiderivative of f prime is just f. So that gives us f, and then what do we do? Yeah, you write the function twice actually, and you do the top minus bottom, b minus a. So the fundamental theorem of calculus states that if you want to take an integral, you take the antiderivative of f prime, which is simply f. Again, oh, I already erased it. But the antiderivative of f prime is the original f. And then you plug in the upper limit and the lower limit, and you subtract. So that's the fundamental theorem of calculus. We also did a problem where they rearranged those terms a little bit. So then what was the fundamental theorem of calculus part 2? Something else fundamental that they wanted us to know. What's kind of the big picture idea about the relationship between the integral and the derivative? Yeah, they cancel out. So the second fundamental theorem, let's see if, or part 2, I should say. Let's go back and actually look at it. So I'm writing it down right, but there we go. The second, part 2 of the fundamental theorem of calculus states that if you're doing an integral, but then you take the derivative, then those two symbols cancel out. So I have there what they have down. Oh yeah, I don't even need the prime this time, because if I now take the derivative, then the derivative and the integral symbol cancel out, and you simply have, oops, that's a to the x. You simply have f of x. The important thing to note there is that our integral is in the variable t, and it's going from some value a up to x. So then, oh, no, they do have that. I'm sorry, that's dx. Wait, I should just write this down the way they have it. D over dx, and then the integral from a to x of f of t dt. Okay, there you go. So then the integral and the derivative cancel out, and you're just left with the function of x, which is the function of the upper variable. The function of the upper variable. So that's the fundamental theorem of calculus part 2. And we probably just want to have those formulas out. You know, have these formulas out on a sheet so that you can always reference them. Is that it? Yep. Okay, so that's what we did last time. So let's go ahead and keep going. What is today? It's not the 14th, is it? Is it the 14th? Oh, that's November. That's the wrong calendar anyway. Boy, I hope it's not November. Okay, there. Nope, that's wrong too. Geez, I need to update our calendar. I'm so sorry. I have no idea where we are though, because I don't have a calendar. Silly me. Well, we can infer. What section are we on? 3.2? 3.3. Okay, so we're fairly early on, and today's date is April. What? Geez, I can't even see the. Oh, the 10th. All right. So this is where we are then. November 7th. That should actually be April 10th. So we still have many, many, many days of lessons to go before we're going to review and then take our last test. And then the way it's scheduled. Wait. This calendar is all wrong. I'm just going to go back to the original. There we go. Here. There's our calendar. Okay, so here we are. It's April 10th. We have many days of class to go, and then we have a review, and then a test, and then our final exam review, and then the actual test. Okay, so that's where we're at. Sorry for that confusion. So today, what do we get to do?
How long is the video now?
4 or 5 pages.
5 problems.
Yeah, only one problem. Wouldn't that be stressful? Okay, did I tell you the cowboy joke yet?
No.
All right, so here's your joke for the day. Why did the cowboy get a wiener dog? Why did the cowboy get a wiener dog? He wanted to get along, little doggy. Get along, little doggy? No?
I get it, like get along.
Yeah, get along, little doggy. It's an expression to tell someone to move along. Get along, little doggy. Well, anyway, that's the joke. So these are the formulas we were just talking about. So in section 3.3, we're going to see more antiderivative formulas. Well, we already know one antiderivative formula. That's the antiderivative of the power rule. And we just practiced that a couple times. So now we get to see some more antiderivative formulas. Did I give you a sheet that had all these on it? That's not on the photocopy, is it? Is it on the last page? I didn't give it to you. Well, go ahead and take out a sheet of paper and we're going to start making our own list. That's just as helpful. So these are antiderivative formulas. Okay, ready? The first one on the list is the constant multiple rule. It states that if you take an integral of a function being multiplied by a constant, then that constant can simply come out front and you can multiply it times the integral that you're trying to do. So a constant value can always just be brought outside through multiplication. That's called the constant multiple rule. So if it's just a coefficient, like a 5, you can just take that 5 outside of the integral and then just focus on doing the integral without the coefficient there. The next one is the sum or difference rule. It states that if you want to take the integral of the sum of f of x plus g of x, then you can split it up into the integral of f of x plus the integral of g of x. What's the purpose of these two rules so far? It's to simplify an integral and make it smaller. So instead of having one big long integral, you can break it up into a bunch of smaller integrals with less information inside. So let's go ahead and do an example of that. Let's say that we wanted to do the integral of 5x squared plus 4x cubed. So we'll do both of these rules right now. If I wanted to do that integral, the first thing I could do is split it up into a sum of 2 integrals. So I would just do the integral of 5x squared, and I would do the integral of 4x cubed. This is a benefit, to break a big integral into a smaller integral. And then what can I do with the 5 and the 4?
Fine.
I'm not combine them. The constant multiple rule states that if you have a coefficient, you can bring that coefficient outside of the integral. So now this would become 5 times the integral of x squared dx. And then this would become 4 times the integral of x cubed dx. So I know we just started doing this, but each of these individual integrals now looks much better and much simpler than the original very big integral. We started off with an integral of a big expression, 5x squared plus 4x cubed. Now all we have to do is this little tiny integral of x squared, and then this little tiny integral of x cubed. So we've broken our work down into smaller chunks instead of one large overwhelming chunk in the beginning. How's that? Questions about those two rules together? So that's for any function at all. Next is the antiderivative of the power rule, and we've already seen this one. So if I wanted to do the integral of x to the n, what do I do? What do I do first? I shouldn't have erased it. The first thing you do is add 1, and then what do? Divide by that result. So it's 1 over n plus 1 times x to the n plus 1. You can do that for any exponent at all, except n can't equal -1. You'll see that up here they actually have a typo. They said provided that n equals -1, they mean n is not equal to -1. This is in your textbook, just so you know. So provided that n is not equal to -1, you can do that power rule. Why can't you do the anti-power rule when n is equal to -1? Let's try it. What happens if you do the anti-power rule when x is, or the exponent is -1? What's the first step? You add 1 first, so that would become x to the 0, and then what do? Divide by the resulting power. 1 divided by 0 is undefined. So you can't do the anti-power rule with -1 as the exponent. And that's it. That's the only exponent that you can't do the anti-power rule. Every other value of n will work. In fact, you can even use decimals and fractions when whatever else you like. So if you did the anti-power rule to, let's just say, x to the -3.4, that's fine. You can do x to the power of -3.4. What would the two steps be? First, you add 1. So -3.4 plus 1 is -2.4. And then you divide by the resulting number. So really, truly, you can do the anti-power rule on any function, on any exponent you like, except for -1. -1 is the only one that results in something that's undefined. All right, so that's the power rule. I think there's just a couple more here that we're going to look at. Oh, yeah. Okay, how about e to the x? Do you guys remember what the derivative of e to the x is? E to the x? So what's the integral of e to the x? Also e to the x. So the integral of e to the x dx is simply e to the x. For the same reason that the derivative of e to the x is e to the x. Because an integral is reversing the process of the derivative. Okay, I think we've just about covered all the normal situations that we would come up against, except for that -1 deal. What do you suppose the integral of x to the -1 is? Is there just not an answer? Because we already said you can't do the anti-power rule. That won't work, because if you add 1 and then divide by the result, you're divided by 0, and that's undefined. So any guesses on what the integral of x to the -1 is? Here's another way of writing it. This is really, what's the -1 exponent mean? What do you do whenever there's a negative exponent? You do the reciprocal. So this is really the integral of 1 over x. Where have we seen 1 over x before? What is it, please?
The derivative.
The derivative of what? Do you folks remember doing the derivative? We did do it. The derivative of natural log? What's the derivative of natural log? Here, wait, let me write it the way we've seen it. If the function is natural log, then what was the derivative of natural log? 1 over x. Yeah, the derivative of natural log is 1 over x. So the antiderivative of 1 over x is natural log of x. So if the derivative of natural log of x is 1 over x, the antiderivative of 1 over x is natural log of x. So this is your last formula here. Is that if you want to do the integral of x to the negative 1, you don't use the anti-power rule. Instead, you remember from doing derivatives that the derivative is natural log of x, so the antiderivative of 1 over x is the natural log. So if you have the integral of x to the negative 1, this is really the integral of 1 over x, the answer is natural log of x. How do you feel about this so far? I would say that you want to keep that piece of paper out with you all the time. And in fact, what I would probably do if I were you, like Anna, I'm just going to borrow this real quick. Anna now has all these formulas for antiderivatives up at the top, and you've got plenty of room down here at the bottom left over. What could you put down at the bottom? You could do examples, or since these are all antiderivative formulas, you could put the derivative formulas. Because honestly, it's so easy to confuse the two rules in your head. You get going and you're doing derivatives and you're doing antiderivatives and then you're doing derivatives and then you start confusing the two formulas and you forget which direction you're going. So probably down there at the bottom, I would go ahead and put in your derivative formulas as well, at least a couple of them. So like, let's go ahead and do it right now. If I have f of x equals x to the n, then my derivative of that is nx to the n minus 1. Right? So put that in your notes, just to remind yourself that you still remember how to do the derivative. Or if f of x is e to the x, then f prime of x is also e to the x. So that's another one you want to remember. And if f of x equals the natural log of x, then the derivative is 1 over x. So you probably want to throw those down at the bottom of your page, just so you have that also at a glance, that you'd be able to pull those out and look at it. So let's see if that covers everything. Yeah, that's everything I had up on the board. Oh my goodness, folks, we are about to have some fun. Does anyone know where Daniel is? All right, well, we're ready to get started here? Let's do it. So looking at our notes now for 3.3, we'd like to go ahead and evaluate some integrals. Now, here's the rule. Anytime we're going to evaluate an integral, guess what I also want us to show? Yeah, a graph. Who said that? James? How did you know I was going to say that, James?
That's what we do.
That is what we do. We support all our answers with graphs. So I'll go ahead and pull up here so we can all see it. Here's the graph of 6x plus 4, which is just a real basic, standard, straight line graph. And we're going from 4 to 9. So let me fix my, fix this a little bit. 0, good, 10, and make this go from 0. What are we doing? We're going from 4 to 9? Gosh, why won't it? All right. All right, well, everyone, you can see the graph. All right, so here's our graph, going from 4 to 9. It doesn't show all the details that I wish it would show. But let's go ahead and make a little sketch. So we're going from, let's say, 0 to 10. And what's our y-intercept? 4. It starts at 4. And then by the time it gets all the way to 10, let's give ourselves a coordinate to put right there. It goes from 4 all the way up to 64. So at the coordinate 10, let's call that 64. And then you draw a line. There, so there's our graph. Is that fair? I'm drawing the whole graph covering the region from 0 to 10 so we can see the whole graph, but what are we interested in? We're just interested in going from 4 to 9. So here's my 4, and here's my 9, and then we'll draw that portion in, and we'd like to find that area right there. There. Isn't that pretty? Now, of course, this is fairly, that's fairly straight lined. We could go ahead and find that area by chunking it into a triangle, couldn't we? If we chunk that into a triangle, could it be done? If I just draw a line straight across, where would that be? That starts at 28. So that's 28 right there. How could we find the area manually? How tall is this triangle? How wide is the triangle? Well, first of all, the width is what, 5? And this height is 28. Whereas this height goes from 28 up to 64, so that's 36. And that height is that width is also 5. So far what we have is a rectangle that's 5 by 28 and a triangle that's 5 by 36. So you could use your calculator and calculate those areas real quick. So the area down below is 5 by 28. So 5 by 28, which is 140. And then the triangle up above is 1/2 base times height. So 1/2 times the base of 5 times the height of 36. And so that area is 90. So the total area that we're looking for is 140 plus 90, which is 230. Now, why on earth did I just go through that whole process? Why? Because we haven't even done the integral yet. And we just spent all this time writing up all these formulas for integrals. So clearly we're going to start doing integrals. But so why bother going through this process of drawing a graph and chunking it up and then finding the area? And 2 reasons. Anyone want to take a stab at it? Kristen, what do you think? Why did we draw the graph and find the area?
So you gotta like an estimate.
Yeah, that's one thing. That way we already know what the answer is. We already know what the answer is. So when we actually do this integral the calculus way, we'll know whether or not we got the same answer. And then what's one other reason? To draw the graph? Yeah, to visualize what this is really doing. That's what we're actually doing here. We're finding the area between 4 and 9 of that function between the function and the x-axis. Okay, so now we're ready to do it, folks. We have the integral from 4 to 9 of 6x. Now, let's write this out real official-like. That's really 6x to the 1 plus 4x to the what? What's the exponent on this x? What is it, Wendy? Which is it?
0.
Yeah, 0, that's it. Okay, so that's what we're actually doing. We're doing the integral of 6x to the 1 plus 4x to the 0. And now let's go ahead and do our antiderivative. Now, we don't have to split this up into all those integrals that we just mentioned. You know, we don't actually have to rewrite it smaller and smaller and smaller. We can just go ahead and do the antiderivative. So, I'd like to do the first one. What's the antiderivative of 6x to the 1? Elias, go ahead and do that one for us. What is it?
It's going to be antiderivative.
The antiderivative, so what do you do first?
Add 1.
Add 1, and then?
You just divide by
Yeah, divide by it.
3.
Very good. And folks, I would go in that order. Don't try to do it all in your head and write down the final answer all at once. Just add 1 to the exponent, and then divide by that resulting number. I know we can probably all do 6 divided by 2 in our head, but just write it down so that you can very clearly see that those two numbers are the same. You can always go back in a second and simplify it. Okay, what's the next anti-power rule? James?
Still add 1.
Yep.
So it's
And then?
4 divided by.
Yeah, very good. So there's our antiderivative for both of them. Now, we only did this barely once last time. So the rule is, once you do the antiderivative, we don't continue writing the long s, because the long s is the instruction to do the derivative. I'm sorry, to do the integral. But we still need to capture the information of 4 and 9. So what you do is you draw a vertical line afterwards, and you put the 4 and the 9 back in. So now we want to evaluate that. And what that means is, take this function, plug in the 9, plug in the 4, and subtract what you get. So here's what we're going to do. First, I'm going to clean that up. So that's really 3x squared plus 4x. And I'm going to plug in a 9, and I'm going to plug in a 4, and I'm going to subtract them. And so I'm going to show that by putting in my parentheses first. I know I'm going to plug in a 9, and then I'm going to subtract what I get if I plug in a 4. So I'm providing myself the structure to know that what I'm going to put inside these parentheses is 3 something squared plus 4 something. So right here I'm going to put 3 something squared plus 4 something, and right here I'm going to put 3 something squared plus 4 something. It's just over here I'm putting in a 9, and over here I'm putting in a 4. So right here I put 3 times 9 squared plus 4 is 9, whereas, my goodness, here I'm going to do 3 times 4 squared plus 4 times 4. There. How does that look? Well, thanks, Adon. All right, so that is the fundamental theorem of calculus right there. You do the antiderivative, and then you plug in the upper number, you plug in the lower number, and you subtract what you get. So what is that? What is all that mess? We probably need to use our calculator to actually calculate all of that. So 3 times 81 plus 36. That gives me 279. If our answer was just 279, that's not what the actual answer is. We got 230. But are we close?
Yes.
Yeah, and plus we're about to subtract something. So 16 times 3 plus 16. Now I have 64. And so what's 279 minus 279 minus 64? Oh no, what did I do wrong? What did I do wrong? That didn't work. Did I mess up here?
Maybe.
What?
Maybe.
Maybe? Well, okay, well, I got 215. Okay, so we all got 215. So what did I do wrong up here? If my graph went from 0 to 28, and then it had a width of 5. Yeah, it does have a width of 5. What did I do wrong up there? 5 times 36 divided by 2 is 90. And 5 times 28 is 140. 140 plus 90 is 230. I did something wrong up there. Or the coordinate 4 and 28 go together. Yep. That's what I put on the graph. And then the coordinate 9. Oh, 9 and 58. Look at that. I used the wrong upper limit. It's not 64 up there. It's 9 and 58. 58 is the height. Does that change everything? It changes everything. So that's really 58. The height is really 30. And so 30 times 5 is really 150 times 2 is 75. And then the answer is 215. Okay. So it did work out. Now that's a third reason for drawing a picture, because then you can check your answers against each other. And if you made a mistake, you can go back and find your mistake. So that's helpful to take any given problem and solve it twice. Once visually and once algebraically, I suppose you could say. Okay, questions about that one? Anybody want to ask any questions or share any feelings? All right, well, everybody, let's do the next one. We don't have to draw a picture of this one because it's a fairly similar problem. So we'll just do it directly. The integral from what? 3 to 7? Of 6x plus 2 dx. So let's think about our steps as we do this. Our first step is to do the probably our first step is to write it out better. So that's really 6x to the 1 plus 2x to the 0. Write it out with all the exponents so you can see what the exponents are so that you can actually do the antiderivative. Then we'll actually do the antiderivative. So x to the 2, 6 over 2, and x to the 1, 2 over 1, evaluated from 3 to 7. Folks, please notice that I immediately went from the integration symbol 3 to 7 to the evaluation symbol 3 to 7. This is called the integration symbol. This is the evaluation symbol. Evaluate because we're going to plug those numbers in and evaluate. All right, so now I'm going to clean this up. That's really 3x squared plus 2x. And I'm going to evaluate from 3 to 7. So I'm going to rewrite it as a parenthesis minus a parenthesis. Folks, also notice that writing down parenthesis minus parenthesis is the technical statement of the fundamental theorem of calculus. The fundamental theorem of calculus stated that the integral of a function from a to b is f of b minus f of a. So that's our fundamental theorem of calculus. So in general, this last step of doing the integral, I would recommend you always have a parenthesis minus a parenthesis to remind you that you're doing the fundamental theorem of calculus, which is the antiderivative evaluated at the top number b minus the antiderivative evaluated at the bottom number a. So definitely put those parentheses in. So what did you all get? 3 times 7 squared minus 2 times 7 plus 3 times 3 squared plus 2 times 3. So 147 minus 14?
147.
147? And then what was this one?
No.
Oh, that is the final answer?
No, that's not the one.
161. For that one.
Oh, were you telling me the first part, James?
Yes.
Oh, okay. Yeah, okay, so there, that's, 147 minus 14, so that's 133. And then 27 plus 6, so that's 33. And it turns out to just be 100. Did anyone else get 100? No, what did I do wrong? I subtracted wrong? My goodness. 147. Okay, I'm going to use my calculator and slow down. So that's times 3, and then minus 4. Oh, that's plus. There we go. Thank you. 161. All right, and then 161 minus 33? 128? Oh, good. All right. Well, there we go, folks. That's how we do a basic integral. You do the integration of each part. Okay, well, that's it. There's just 2 problems to do with polynomials. Okay, that was the rule for a polynomial, which is the power rule. We also now are going to do the integral of e to the x functions, and we're going to do the integral of 1 over x functions. So let's keep going and see how it works. So the next one says the integral of 7e to the x dx. What do you notice about this integral? It does not have the little numbers. Very good. So folks, let's write down some vocabulary. The problems that we just did, you might want to turn back. This is called a definite integral. A definite integral. And a definite integral has the lower and upper limits of integration. And what you're calculating, what's the final product?
Area.
An area. So that's what a definite integral calculates an area. So provided you have the little numbers, the upper limit, the lower limit of integration, then your final product is a number. It's an area. Whereas this is called an indefinite integral. And an indefinite integral, you're simply going to compute the antiderivative, and that's it. You're just finding the antiderivative. The beauty of that is, once you're done computing your antiderivative, how do you check your work? Yeah, you just take the derivative of it and see if you get back the original expression. So it's kind of a loop what we're about to do here. You take the antiderivative, you write it down, that's your final answer. And then to check your work, you can take the derivative of it and see if you get what you started with. So this is an indefinite integral. So I have more to say about it, but let's go ahead and do it. First of all, there's a coefficient. What can you do with a coefficient? Yeah, you can just take it outside. You can just take the coefficient right outside the integral. So now we're really doing 7 times the integral of e to the x dx. Now this comes straight out of your formulas. What's the integral of e to the x? It's just e to the x. So it's just 7 e to the x. That was not very exciting. There's not much happened. But that's because e to the x is a nice simple function. Now there's one more thing to say about a definite integral. Sorry, an indefinite integral. And that is, anytime you take an indefinite integral, you write down the answer and then you write plus c, where c is a constant. C is a constant. Now you might say, well, why do you write plus a constant? What might you say? Why would you write plus a constant? Yeah, exactly. Well, let's give another example. You have tons of space there, so let's do one more example. Let's say you just wanted to do the integral of x squared. So everyone, let's go ahead and do that. What's the antiderivative? I would add 1 and then divide by the resulting number. So I claim that the antiderivative of x squared is 1/3 x cubed. However, you have to write plus c, meaning plus a constant. That's how you read that. Plus a constant. Now remember the claim. We just did the integral. So this thing, if I take the derivative of it, what should I get? X squared. So let's go ahead and try. We're going to try a couple. What's the derivative of 1/3 x cubed? You multiply by the 3. 1/3 times 3 is 1, and then you subtract 1 x squared. Did we get the original? We did. Now, but watch this. What if I tell you the function was actually 1/3 x cubed plus 5? What's the derivative of that? The derivative of 1/3 x cubed is still x squared. What's the derivative of 5? 0. Did I still get x squared? Yeah. What if I said that the integral actually was 1/3 x cubed plus 200? What's the derivative of that? Still going to be x squared plus 0, which is x squared. So actually, even though we're saying that the antiderivative of 1/3 x cubed, how many different functions are there in the universe whose derivative is x squared? How many, technically? Infinitely many. Infinitely many. Because what constant can I put right there? Anything. Any number I want. I can put pi right there. I can put -7 right there. I can put anything. So the answer to an indefinite integral always has a plus a constant at the end. Because technically, when you turn around and take the derivative of this thing, what's the derivative of a constant? 0. And so it goes away. All right, I'll tell you a couple things about this. 2 funny stories. I hope you think they're funny. Going all the way back to when I was taking calculus, 100 years ago when I was in high school. The plus C, all of us forgot. The whole time. Throughout the whole semester, we had the same teacher for a whole year doing calculus. We would all do integrals, and we'd all forget to put a plus C. And she would grade all of our papers with a red pen, and she'd always write, plus C! Because we always forgot to write it down. And so in the end, we all made T-shirts that just said, plus C! And then we would wear those T-shirts to her class. Because we always forgot to write plus C. We actually had a joke that when she graded our test, she would write plus C, and then she would also write things like, no! So we all joked that she had, oh no, she didn't write no, she wrote boo. Boo! That's what she would write. If we forgot to write the plus C at the end of an integral, she'd write boo! Which reminds me of the scene from The Princess Bride. Do you remember that scene where she's having a nightmare and she's there at the castle, and there's an old haggardly woman yelling, boo! Boo! Do you remember that scene? All right. Well, anyway, our teacher would always write boo, so we would joke that she had a boo bat, that she would come at us if we didn't write plus C. She'd have a bat with the word boo written on it, and then she would come over and hit us with it because we kept forgetting to write plus C. Okay, anyway, maybe this is too much story time. I just wanted to say that whenever you do an integral, you write plus C, because technically when you take the derivative of this, the C goes away and you get the original function. All right, that was one thing. So let's go ahead and try another one, folks. The next one was what? The integral of 2 over x. The integral of 2 over x. Is this a definite integral or an indefinite integral? It's indefinite, meaning there's no limits of integration, so we're not calculating an area. We're simply going to find the antiderivative, and we're going to write plus C at the end. So what's the antiderivative? What's the first thing we might do to make our lives easier? Because we do not have a formula for 2 over x. We just have a formula for 1 over x. So what can I do with the 2? What can I do with the 2?
X to the power of negative.
Well, you could bring the x up if you want, but we have a formula for the integral of 1 over x. So we definitely want to keep the x down in the denominator. But how can I rewrite the 2? Isn't this really the integral of 2 times 1 over x dx? And since 2 is a coefficient, what can I do with it? Bring it outside. So we're really going to do 2 times the integral of 1 over x dx. Yeah, so anytime you see a coefficient at all, if you want to, you can go ahead and bring that coefficient outside. It's a helpful beginning to the problem. Okay, so then what is the integral of 1 over x dx? The natural log. So that's 2 natural log of x. And now what do we have to write technically?
Plus C.
Plus C. Plus a constant. And so now, again, looking at our notes here, an indefinite integral, the product that you're creating is an antiderivative. I claim that 2 natural log x plus c is the antiderivative of 2 over x. How do I check that it really is? How do I check that my answer is right? You take the derivative. So the derivative of natural log of x is 1 over x, so that's 2 times 1 over x. The derivative of a constant is 0, and so my answer is 2 over x. So when you do an indefinite integral, you're simply finding the antiderivative, and then you immediately check your work by taking the derivative and seeing if you get the same thing back. And just to demonstrate that plus c again, what if the function had actually been 2 natural log of x minus 100? What's the derivative of that? It would be 2 over x plus 0, because the derivative of negative 100 is 0, so you still have 2 over x. So again, how many different functions have a derivative of 2 over x? Infinitely many, depending on what value of c you have right there. All right, so that's the difference between a definite integral has limits of integration, which means you move to the evaluation bar and actually calculate an area. An indefinite integral is simply producing the antiderivative, which has a plus c at the end, which you can check your work by just taking the derivative. Okay, I'm going to tell you one more story because I can't help myself. When I was in calculus, the teacher got to this day, this very day, and she said, there's two different types of integrals. Okay, and so do you all see that? There are two types of integrals. You've got this type where you actually calculate an area, and then you've got this type where you're simply writing down the antiderivative. So here's what she did. She said there's two types of integrals, type 1 and type 2. And I stopped her right there and I raised my hand. I said, well, what are the two types called? And she said, I don't want to tell you that. I don't want to confuse anything. I'm just going to call it type 1 and type 2. And I raised my hand again. I said, well, yeah, but maybe just what are their names? Like instead of writing type 1 and type 2, like I just want to write the name down. She said, I'm not going to tell you. I think it'll confuse everyone. Let's just keep going. And that was the day I lost faith in humanity. Right? What was I asking for, folks? All I wanted was the name to write down. So I just knew what the name was instead of type 1 and type 2. And I've been kind of damaged ever since then. You know, can you appreciate that? Like, teachers are supposed to answer questions, but she didn't. Anyway, let's keep going. So here we go. We want to take the, number 5. We're taking the what? What type of integral are we taking? The what? The number 5? Indefinite. Okay, maybe I just wasn't hearing you correctly. Yeah, we're taking the indefinite integral. And since number 5, let's go ahead and write that right now. For number 5, it's the indefinite integral, which means we're going to write plus c, because we're doing the antiderivative. So we do the integral of 6x squared. Now I'm writing this down for the first time, so I don't need to fix anything. It's ready to go. So everybody go ahead and do the anti-power rule. It's ready to go. The anti-power rule. So remember the rules. You add 1 to the exponent and divide by the resulting exponent. Yes. Just so you know, you don't have to do it like that. But it's fine if you did. You know, here you go. So then here you raise that you wouldn't have both. There you go. Yeah. There you go. And plus, now that you have done the integral, you get rid of the because you already did it. So you erase the long x, and you can just put a multiplication of it. There you go. There we go. Yeah, now you're done. So now the integral was accomplished, and you have your answer, which you can clean up a little bit. You know, 6 over 6 times a third, you can clean up. Or 6, you can clean up. And then when you're all done, plus c. Yeah, okay, very good. Okay. So anti-power rule, 6x squared. Karina, what did you get for 6x squared?
2x3.
Yeah, yep, because you're going to add 1 and then divide by 3, so that's 2x to the 3. And then what's the anti-power rule for the next one, Ashley? Say that again? Yes, 2 over 3 x to the 6th. So that's it, folks. It's 2x cubed plus 2/3 x to the 6th plus a constant. And what we're claiming is that if you take the derivative of that, you should get back the original function. And more importantly, if you take the derivative of a constant, you get 0, so that goes away. And then, yes, the derivative of those, you could go ahead and try it. The derivative would be 6x squared plus 4x to the 5th. So, yeah, you do get back the original. And that's called an indefinite integral. We didn't actually calculate an area because we didn't know the limits of integration. We just produced the antiderivative. Okay. Ooh, number 6 looks really exciting. Is it definite or indefinite? Yeah, this one is definite. It's definite because, I mean, I guess I don't know why they use the words definite and indefinite, but with definite, you're definitely calculating an area. You're defining your limits of integration so you can calculate an area. So this is a definite integral. Okay, what do we do? Do we have a formula for 1 over x squared? No, we don't. So how do we rewrite 1 over x squared? Just like before with derivatives, you always have to rewrite it as a normal exponent, not in the denominator. So how do we rewrite that? Yeah, it would be the integral from 4 to 5 of x to the negative 2 dx. So just like before when we were doing derivatives, you always had to surface that denominator variable up to the numerator so that you could do the power rule, or in this case, the anti-power rule. So it's a little trickier once you have negative exponents. I always recommend checking things on your calculator. What's negative 2 plus 1? Negative 1, and then divide by the result. So 1 over negative 1. And now we just did the integral, so we don't do the integration symbol again. We do the evaluation symbol from 4 to 5. And I suppose we could clean that up a little bit and just write negative. Actually, we can clean that up a lot. What could we write now? The 1 over negative 1 is just negative. And what's x to the negative 1? So is that it? Is that a clean way of writing the answer? Because 1 divided by negative 1 is negative, so my answer is negative. And x to the negative 1 is really 1 over x. So the answer is negative 1 over x. That's a really nice, clean way of writing it. All right, so now what? The fundamental theorem of calculus says you're going to do something minus something. We're plugging in the top number, and then plugging in the bottom number, and then subtracting. So what do we have? Negative 1 over 5 minus negative 1 over 4. So we have a double negative there, so that's really negative a fifth plus a fourth. Now, folks, at that point, you can type that into your calculator. Right? You can just type it in, you could get a decimal, or you could just do the decimal in your head. That's negative 0.2 plus 0.25. So either way, the answer is 0.05. Or you could even find a common denominator if you really wanted to. You could find a common denominator, so that'd be 5 and 4 going to 20, so negative 4/20 plus 5/20, and so the answer is 1/20, which is the same as 0.05. So there are a lot of different ways you could do it. You could even, into your calculator, type in negative a fifth plus a fourth, get an answer, and then hit math frac. You all know the button math frac? Have we talked about math frac? Oh, math frac is one of the best buttons you'll ever know. Folks, go ahead and do on your calculator negative 1 divided by 5 plus 1 divided by 4. You get the decimal 0.05, and then you hit the math button. I've really not talked about math frac?
Yeah.
I have talked about math frac. I think I have. Well, you hit the math button, which is the craziest button name for a calculator ever, because seriously, aren't they all doing math? So you hit math, and then the first option says frac, which sounds like a bad word, but it's not. Frac stands for fraction. And you hit enter, and it tells you 1/20. So the math frac button on your calculator will convert a decimal to a fraction. And in a case, there's your answer, 0.05. A lot of different ways to get there. Do any of you guys watch Battlestar Galactica? The new one from a few years ago? In Battlestar Galactica, it's this future time period where they're all on spaceships, and their bad word is frac. So they'll say fracking and frac, and I always kind of laughed in my head that they were saying frac, short for fractions. Yeah. All right. So now, of course, folks, that one would have been a good one to actually look at. What is it that we're really doing? We're finding the area underneath the graph 1 over x squared. Look at that graph. See, that's a fun graph. Look at it. We're finding the area between 4 and 5. Now, folks, look at this graph. First of all, how much area is there between 4 and 5? I mean, virtually nothing, right? And of course, what was the answer? 0.05. So even if I zoom in a little bit and I get down there and I look between 4 and 5, even now, how much area is down there? Yeah, 0.05, not very much. So the graph confirms what we calculated. There's not much area down there. Now, look at the power of Desmos. I can do a function integral under miscellaneous integral, and I can type in the integral from 4, oops. I can type in the integral from 4 to 5 of 1 over x squared. And then I can hit enter. Oh, wait. Oh, dx. There. And it tells me the answer is 0.05. So, folks, do you think Desmos would be helpful when you're doing your homework? Yeah, very helpful. I mean, keep in mind, you can't use Desmos while you're taking a test, but you can use Desmos to figure out what the answer is, and then you can go back and make sure your work produces that answer. So this is a way for you to check what the answer is. Okay, so just looking ahead here, we have a couple more integrals to try of various types, and then I think there's a word problem, and then that's it. Okay, so let's take a break. The time is 12:02. Let's come back at 12:12. So Anna, who's watching your baby right now?
My mom.
Oh, how nice.
Yeah.
Does she text you, like updates?
Yeah, she always sends me pictures of what they're doing.
Oh, good. Yeah, us too.
Yeah, you. I guess because I wasn't here. I didn't. Oh, this is the first one, right? You can take a picture of them. I'm sorry. Which word? That's gonna help a lot. Okay. I think we'll get it once. That's it. I'm just. Did I not even start it? Oh, yeah, you just missed it. But it's so weird. Doesn't it? Oh, you can go back to do it. Did we? I think so. I don't remember what I had to do. What it's doing is just. Yeah. And then you say the videos help explain it better. I haven't done it. No. I was trying to touch this also with this with yeah. Give me extra time to finish some of the assignments. I'm doing okay. Did you like review the table her like her ACC 330 test? Yeah. But she gave us all the credit. That's what she's doing. What? Pretty much everything for the test. Yeah. She wasn't gonna do it when I was software. No, she's doing it with the rest of her. But the best people have. You're looking for this one. So that's just the points. I'm gonna check the videos today. Because I have a lot of catching up to do because I have to do this stuff that is and then I have a night class. You know, it's like a fast paced one, so you have to do the function and like the other. But luckily I'm so behind.
All right, is everybody back?
Yeah, this one is there.
Let's keep going. Now, folks, these next few problems, I'm going to help you set them up, and we just won't finish them all the way because I want to make sure we have time to do the word problems at the end. So take a look at number 7. Number 7 is a perfect candidate for a question on the test because it's fairly complex. So first of all, is it definite or indefinite? Indefinite. All we need to do is find the antiderivative. Now, let's go ahead and rewrite this in the form it needs to be. So 6x squared is good. That's good to go because it's a variable to an exponent. How do we rewrite 4 over x so that it's a variable with an exponent? Yeah, 4x to the negative 1. Now actually, as soon as I just said that, that's wrong. Do we have a formula for 1 over x? Yeah, that's the one. We don't want x to the negative 1. That's the one we're not allowed to have. Yeah, so I'm actually just going to leave that as 4 over x, because that's what we can actually do. Or if you wanted to, you could write it as 4 times 1 over x to more clearly point out that in that case, you're going to use the formula that the integral of 1 over x is natural log. Okay, but now how do we rewrite 4 over x cubed? Yeah, that would be x to the negative 3. Notice how I'm chunking the coefficient off of it. I mean, you don't have to chunk the coefficient off of it, but we're going to be focusing on doing the antiderivative of the variable part because the coefficient just comes along for the ride. So that's 4x to the negative 3. And then, how do you rewrite the square root of x? X to the 1/2. So that's the integral we actually want to do. And actually, we will go ahead and finish this one because it's pretty complex. So let's do the integral of each part, applying all of the rules appropriately. So the first one is just the anti-power rule, right? So you add 1 to the exponent and divide by the resulting coefficient. I'm always going to do it this way. I'm not going to do 6 divided by 3 in my head and write that down. I'm just going to write down add 1, divide by what you get, because I'm going to go to the next step to simplify. I encourage you all to do the same thing. One thing at a time. Don't try to do the antiderivative and simplify it as you go. I mean, you can. I just think it's risky. Okay, what's the antiderivative of 1 over x?
Natural x.
It's just the natural log of x. So now that one is minus 4 natural log of x, because the coefficient comes along for the ride. Okay, how about the antiderivative of x to the negative 3? Very careful, we want to add 1. So that's x to the negative 2. And then divide by what we get. So that's negative 4 divided by negative 2. This is another reason just to write it down and not try to do it all in your head all at once, because you have 4 over 2 to simplify, you have a negative over a negative to simplify. That's a lot. Okay, and then the last one, the anti-power rule, you add 1. So 1/2 plus 1 is what? Keeping in mind that instead of adding 1, you can add 2 halves. So what is it? Yeah, x to the 3 halves. And then we have to divide by 3 halves. So what's 5 divided by 3 halves? Now see, again, I'm just going to write it down. I just write it down. 5 divided by 3 halves. Because I can always go back and do a little scratch work and figure that out later. But right now, I did it. I have done the antiderivative. I'll go ahead and write plus c. And now it's just a matter of going back and simplifying all of that. So I have a 2x cubed. I have a minus 4 natural log of x. I have a plus 2 over x squared. So the negative 4 over negative 2 is positive 2, and x to the negative 2, I drop it to the denominator, so it's over x squared. Okay, so now what is 5 divided by 3 halves? Yeah, so 5 divided by 3 halves is really 5 times 2/3, which is really 10/3. Did everyone get 10/3? All right, so now that's plus 10/3 x to the 3 halves, which you can just leave that one plus c. So in terms of how to simplify, we definitely want to drop things into the denominator again so that it's clean and you don't have negative exponents. But you can leave the x to the 3 halves. Just so you know, in Math AS, they might simplify that to look like 10/3 x root x. How did they do that? Why is x to the 3 halves the same as x root x? Let's look at x to the 3 halves. What is that? There's a couple different ways to think about it. You could either, what's the denominator of a fractional exponent represent? The root, and the numerator represents the power. Have we done this together? And so this is really the square root of x cubed. And then what? How do you simplify a square root of x cubed? That's really the square root of x times x times x. I don't know if you guys have seen this method of grouping. But since we're doing a square root, anytime you see two of them, a pair of something, you can take it out. And so you're left with x root x. Have you seen this method of grouping? Okay, maybe you haven't. Well, that's fine. The other way is you could chunk that up. You can have, instead of the square root of x cubed, you can have the square root of x squared times x to the first, which that root then separates into the root of x squared times the root of x. And what's the square root of x squared? Just x. So that's a variety of different ways that you can simplify that. Another way that you could think of doing it, I'm basically showing a lot of different ways, so hopefully all of you will find one way that you like. You could do the square root of, well, yeah, actually, I think that is what I wanted. Well, yeah, those are really the only two ways. Oh, you could write it like this. X to the 3 halves is really x to the 2 halves times x to the 1 half. How about that? You remember your exponent rules that when you multiply two numbers with the same base, you add the exponents? So 2 halves plus 1 half is the 3 halves that we want. And so now this part is really just x to the 1, which is just x. This part is the square root of x, and so you get x root x. Okay, so there's 3 different ways you can think about it. You don't have to do it all 3 ways. I just hope that you find one way that works for you. Okay, well, that's the final answer. The next one, I'm going to leave that for you. Number 8 is for you to try on your own. Number 9 is a good one. Let's do it. I mean, they're all good, but let's solve it together. So what about this one? Is it definite or indefinite? This is definite because they gave us the numbers of integration, so we're calculating what? An area. Okay, so first of all, what can we do with that 3 since it's just a coefficient? We can take it outside, so it's just the integral of 1 over x dx. I really recommend you do that whenever there's a coefficient, you can just take it out. So do we have a rule for the integral of 1 over x? Natural log. So this now becomes 3, and watch what I do with my big brackets. 3 times the natural log of x evaluated from 1 to e to the 7th. Because the 3 is getting multiplied by whatever the answer of that integral is. So I'm chunking off the result of that integral in brackets so that I remember when I'm all done doing that, I need to take that answer and multiply it by 3. So what does the fundamental theorem of calculus tell us? To write down parenthesis minus parenthesis. We're going to plug in the upper limit, plug in the lower limit, and subtract. So what does that give us? Natural log of e to the 7th minus natural log of 1. Both of those you could type into your calculator. Very careful. You could type in natural log of e to the 7th, and then you could type in natural log of 1. But perhaps it's easier if you just remember what the natural log stands for. Everyone, this is a real quick review of natural logarithms. A natural log, let's say I'm going to do natural log of e to the 7th. The natural log is really log base e, right? And remember, traditionally, okay, let's review how to read a logarithm. Log base 2 of 8. You read this, first of all, by saying log base 2 of 8. But what does it mean? It means 2 to the what equals 8? That's the question. 2 to the what power is 8? So 2 to the what is 8, folks? 2 to the what power? 3. 2 times 2 is 4 times 2 is 8. So 2 to the what is 8? 3. So log base 2 of 8 equals 3. Okay? We haven't done a lot of logs in this class, but this is the definition of what a log means. You take the little number, the big number, and if you read the little number to the what is the big number. So log base 2 of 8 means 2 to the what is 8, the answer is 3. So what does this mean? E to the what is e to the 7th? 7. Right? E to what power is e to the 7th? E to the 7th power is e to the 7th. So that answer is just 7. And I hope that all of you go ahead and type it in your calculator. Do natural log of parenthesis e to the 7 and see if you get 7. Natural log of e to the 7th. You have to use parentheses though. Make sure you type in natural log parenthesis e exponent 7 parenthesis, and you should get 7. Yeah. All right, so that's just 7. Now what about natural log of 1? How do we interpret that? That's really log base e of 1. So e to the what is 1? E to what power is 1? Someone said it. 0. E to the 0 is 1. So that's just 0. Of course, you can type that into your calculator as well and see the natural log of 1 is 0. So what are we left with? Yeah, 21. 3 times 7 is 21. Now, that's a good one to look at. This is a real good one to look at, like the graph that is. So first of all, I'm going to go ahead and calculate what on earth is e to the 7th. That's 1,096. So e to the 7th is 1,096. So I'm going to look at the graph 3 over x from 1 to 1,096. That's pretty crazy. So let me fix my axis here. I'm going to make my y-axis go from 0 to 50. And my x-axis go from 0 to 1,096. So I'll just say 1,200. There. Oh, well, it's not a great graph. How much area is underneath that graph? I mean, where do you even see any area under the graph? Just this little corner right here? It's just that little teeny corner where you can see some area. So maybe I should zoom in a little bit. Where's most of the area of the graph? Just right here. This is where the bulk of it is, because now if I go off to the right, it's mostly asymptote. There's not much area over here. You're not gaining a lot of area by looking all the way out to 1,000. In fact, most of the area occurs under the graph right there at the beginning. So in fact, check this out. What if I did the integral from 1 to simply 100? Not even 1,000, just 1 to 100 of 3 over x. Then what would that area be? It would be 13.8. What was our area? 21. So there is still area going all the way over there in that asymptote, but most of the area was already located here, between 1 and say 100. Okay, but now if I go up there and I type in e to the 7th, oops, that's 3. I want e. There we go. It gives us exactly 21. So it's what we expected, and that's the area that we just found. Okey-doke. Folks, you can do number 10, because it looks like one we've already done. So you can actually do number 11. That looks like one we've already done. So how about 12? How do we do number 12? When you look at number 12, what are you tempted to do? Not cry, not run away, not skip it. What are you tempted to do? I think I'm hearing FOIL. Is that what you said? Okay. Yeah, so FOIL would be one thing to do, because in fact, we don't have an integration rule for product rule. Remember the product rule? Derivative of the first times the second plus derivative of the second times the first. If we were taking the derivative of this, you could do the product rule. But even better would be just to FOIL it out. So everybody, let's FOIL that out so that we can see that the problem is actually the integral of x plus 4 times x minus 2 dx. So that's really the integral of x squared plus 2x minus 8. Is that it? Yeah. So that's it. You still solve that one using the anti-power rule. Is this a definite or indefinite integral? It's indefinite. So let's just take a look anyway. Here's my graph of x plus 4, x minus 2. Whoops. There. And what does it look like? Oh, there it is. It's parabola. Boy, I wish there was a better way to change the axis. It's so time consuming. You can't even use the tab button. It's terrible. You can't even double click to highlight it. You have to put the cursor to the left, drag it over. Oh, what was me, what was me. All right, folks, so there's our parabola. So what area are we trying to find? Yeah, between the function and the x-axis. In this case, did they tell us where to look? No. So actually we have no idea what area because they didn't tell us where to look. But as soon as they tell us where to look, then that's what we would be finding is the area trapped between the function and the x-axis. I want you to look at this now. Draw a picture with me. Draw a picture with me. Here's what they're asking us to find is the area trapped between the curve and the x-axis. So this is really fun. Everybody, you draw a little parabola. Okay, little parabola, buddy. So the area that we're looking for is either this area trapped between the curve and the x-axis, or this area, or this area. Right? Isn't that fun? Isn't that strange? We're always looking for the area trapped between the function and the x-axis. So technically in this region, we would be calculating what? A negative area. In this region, we'd be calculating a negative area. Whereas in this region, a positive area, and in this region, a positive area. Oh my gosh! I think I just created the next cool alien for the next Star Wars movie. Look at that! Doesn't that look like a fun alien that you'd see in Star Wars, the movie? I think it does. It's like a little bloop, bloop, bloop fella. That's not just me, right? That looks like an alien.
Okay.
Okay.
I like Alien versus Predator.
Like an alien what?
Versus Predator.
Yeah, it could be that too. All right, so anyway, just as a reminder, that's what we're always doing is finding the area between the function and the curve. Okay, we've got one more tricky one and then a couple of word problems. So we want to find, is this definite or indefinite? Definite, because we're finding an area. Now folks, I hope you appreciate, how does that look? Pretty tricky, right? This looks like hard math, right? Like out in society, if people saw that on a piece of paper, they'd be like, whoa, math, I'm not a math person, right? But are we about to do that integral? Yeah, we're about to do it. Is it hard? No, it's not hard. Anybody can learn this stuff, folks. Math is not tricky. You just, once you know how to do it. So what should we do? What do you think we should do? Notice that it looks like a quotient. Hody high minus hidey ho all over ho ho. But that's a derivative rule. We don't have a quotient rule for integrals. The only rules we have are these. That we can do the anti-power rule, the e to the x, and then 1 over x. Which rule could potentially apply? Here's another question. What technically makes this problem hard? What one piece? The denominator, the square root of x in the denominator. Can we move that somewhere? Can we get rid of it? Can we change it? Yeah, let's see if we can manipulate this a little bit. This is really 6x squared plus 8 all over x to the 1/2, right? But then what else? Can we somehow switch this, not just one big fraction, but into two small fractions? I mean, two individual fractions? What do we do next? Can we split a fraction like this?
Yeah.
We can. So this is really 6x over x to the 1/2. Sorry, that's 6x squared. Plus 8 over x to the 1/2. Then what? Now that we just have individual fractions, can I bring the x to the 1/2 up to the numerator? Yeah, so that first one would be 6x squared x to the negative 1/2. And then the next one would be 8x to the negative 1/2. Folks, this is a lot of manipulation. Consider, we're doing all this work just to manipulate the expression into a form that we can actually use. We haven't even done the integral yet. Finally, how do I combine these? X to the 1/2 times x to the negative 1/2. What do you do when you multiply two numbers with the same base? What do you do with the exponents? You add them. So finally, we have, what's 2 minus 1/2? 1 1/2. 6x to the 3/2 plus 8x to the negative 1/2. Now can we do the integral of that? Now we're ready. I'm going to put my integral back in. My integral from 3 to 5 dx. That was a lot of work just to get to the point where you could do the integral. You might say, well, gee, why didn't they just give us the problem like that? Right? But calculus is a little mixture where you're being tested on your ability to do an integral, but you're also being tested on your ability to manipulate expressions. That was just a joke. Okay, so now what do we do? Anti-power rule? Has everybody done one today? Mario, I don't know that you've done one. Do the anti-power rule for us with x to the 3/2. Add 1, so that's plus 2 halves, so we get 5 halves. Yeah, and then divide 6 by 5 halves. Okay? And then what about the next one? I think everybody's done one. Anna, have you done one? So anti-power rule, what do?
You add 1.
Add 1, so plus 2 halves, that gives us x to the positive 1/2.
And then you put 8 over and divide.
Yeah, and then 8 divided by 1/2. And at that point, we did the integral, so now I put my evaluation line from 3 to 5. Now, there's still a lot to clean up, isn't there? Like, all I did was just write 6 divided by 5 halves and 8 divided by 1/2. I'm just writing down what the answer is, and now I have to go back and actually do all that. So I'll go ahead and do my calculation somewhere else. 6 divided by 5 halves is 6 times 2/5, which is 12/5. And then 8 divided by 1/2 is 8 times 2 over 1, which is 16. So now I have 12/5 x to the 5 halves plus 16 x to the 1/2 evaluated from 3 to 5. All right, so now we're ready to do the fundamental theorem of calculus. The fundamental theorem of calculus tells us to do parenthesis minus parenthesis. And what are we going to put in? We're going to put in 12/5 5 to the 5 halves plus 16 times 5 to the 1/2 minus the exact same expression, 12/5 of 3 to the 5 halves plus 16 times 3 to the 1/2. What's the best way to type that into your calculator? Lots of parentheses. Yeah, absolutely right, Mario. Lots and lots and lots of parentheses. And if you do it correctly, you can type in the whole expression with a 5 and then hit second enter. It will pull back up the whole expression already there, and you can just change it all to a 3. So I'm going to show you the proper way to put this in with parentheses so you can write it down. It would be parenthesis 12 divided by 5, parenthesis, parenthesis, 5, caret, parenthesis, 5 divided by 2, parenthesis, parenthesis, plus 16, parenthesis, 5, caret, or parenthesis, caret, 1 divided by 2, parenthesis. All right, so that's what it would look like in your calculator if you're doing it safely. You know, like really safe, playing it safe, putting everything in parentheses. And plus, when I'm all done, I can hit second enter and just replace the 5s with a 3. So my first answer was 169.9411. And then second enter, go back up, change my 5s to 3s. That took very little time, minus 65.12511. And then since both of those numbers are right there on my screen, I'll go ahead and subtract using all the decimals. And I got 104.816. Did anyone else get that number? You got that, Luis? Now, of course, how do we check? We graph it, of course. Like, what does this graph even look like? It's 6x squared plus 8 divided by the square root of x. So here's the graph. Oh. And the graph is really not that exciting. It's just something that looks like a parabola, except one side of the parabola is actually a vertical asymptote, and the other side of the parabola goes off to infinity. So how could I make that look better? I go up to 300, and I'll go to the left, it's 5. Go up 200. Nope. There we go. That's what our graph looks like. And I just want to go between 3 and 5. So with Desmos, I can actually type in a vertical asymptote and another vertical asymptote and actually zoom in on just the area that we're interested in. So I'm just looking at this area between 3 to 5 right there. I wish I could shade it in. Oh my gosh, what if I can shade it in? No. That was too much. Darn. I wonder how to shade that in. If it was greater than 3, less than 5, and y less than that. Okay, well, I've shaded a whole bunch now, but it's this region where it's shaded from all 3. So that's the area we just found. So now I can go ahead, type in the integral. Here's my integral symbol, and I'm going to go from 3 to 5. Type in dx, and wow, the answer is 104.816. Oh boy. Confirmation that we got it right. Okay. You'll definitely have one like that on your test, because it's a good, solid, long, lengthy problem. All right, folks. We've got 2 word problems here. Let's take a look. Hopefully we can do both. So it says the traffic flow rate of cars per hour across an intersection is given by this. R of t equals 500 plus 600 t minus 150 t squared. Now let's consider what they just told us. What is that calculating? Yeah, cars per hour. Okay, they're calculating cars per hour. Notice cars per hour sounds a lot like miles per hour, like a velocity. Miles per hour, it's a speed. This is cars per hour. So in terms of f of x, f prime of x, f double prime of x, referring to distance, speed, and acceleration, which one did they just give us? Since they're saying cars per hour, the analogy is that it's this one. They're telling us cars per hour rather than miles per hour. And therefore, if I go from this function and I go up to do the antiderivative, if I go from speed to distance, what's the antiderivative of cars per hour? Notice here, miles per hour becomes miles. The antiderivative of miles per hour is just miles. So the antiderivative of cars per hour is cars. So that's what they're interested in calculating. If you know the flow rate of cars per hour, then you should be able to calculate how many cars just went past this intersection. That's what they would like to know. How many cars went past the intersection? So this technically is f prime of x. And they're going to ask us to do an antiderivative. So let's read it. The traffic flow rate is given by that, where t is in hours and t equals 0 is 6 a.m. How many cars pass through the intersection between 6 a.m. and 8 a.m.? So let's draw a fake graph. There's my flow rate. And they said that 6 a.m. is t equals 0. So what's 8 a.m.? That's 6 a.m., 7 a.m., 8 a.m. What's 8 a.m.? 2. So we're going from t equals 0 to t equals 2. And so technically what we're about to calculate is this area right there. Notice I said fake graph because I just drew a squiggly line. We're just trying to capture the area beneath it. And the area beneath it is going to tell us the total number of cars. This is the flow rate of cars per hour, so the area is going to represent just cars. So what do we do? We want to take an integral from 0 to 2 of that function. So we're going to take the integral from 0 to 2 of the function 500 plus 600t minus 150t squared dt. Yeah. Would we do that what? Yeah, absolutely, the antiderivative. Yeah. They gave us a function which represents a rate, and since it is a rate, the antiderivative of that is going to tell us how many cars went through the intersection, which is what the question says. How many cars passed through the intersection? So we'll go ahead and do an antiderivative. You might want to write that as 500 t to the power of 0 plus 600 t to the power of 1 minus 150 t to the power of 2 dt. And then we go ahead and do the anti-power rule. So adding 1 divided by 1, add 1 divide by 2, and add 1 divide by 3. So for your antiderivative, did you get 500t plus 300t squared minus 50t cubed? Evaluated from 0 to 2? Did anyone else get that? So then what? You what?
Plug and play.
Yeah, you plug in, and I'm going to put my 2 parentheses. So I've got parenthesis minus parenthesis. Now, folks, at this point, you don't have to write all that down. That's very time-consuming to write all that down. You can do all that in your calculator because we're just doing substitution, right? Substitution is a calculator activity. So 500, again, use parentheses so that you can plug in the 2 and then plug in the 0. Of course, you folks already know what happens when you plug in 0. What happens when you plug in 0? Yeah, the whole thing is just 0. So did you get 1800 minus 0? Did anyone else get 1800? Yeah. Now, does that sound reasonable? After all, what if we did a left-hand Riemann sum? What if I did a rectangle and another rectangle? So I'm just going to go ahead and find the flow rate at time 1 and the flow rate at time 2, and I'll calculate the area of those. So if I take my original formula, 500 plus 600 times 1 minus 151 squared, the flow rate at hour 1 was 950, and the flow rate at hour 2 was 1100. And so if I just use those as approximations, 1100 plus 950 turns out to be 2050. And is that relatively close to the answer we got? Yeah, relatively close. If I just use the flow rate at the hour of 7, 8 as a representation of the whole, it's pretty close. Folks, I know that we're almost done, so let me just point out to you how to do the last one. It says that the marginal cost function is c prime of x, which is 11 over root x. Again, notice that they're giving us the derivative, which means we're going to do the antiderivative to calculate the original. Right? We always do the antiderivative of the derivative to get the original. So it says the company's marginal cost function is 11 over root x. How do you rewrite that? It's really 11 over x to the 1/2, which is really 11x to the negative 1/2, so that you can apply the power rule, the anti-power rule. And it says find the total cost of the first 49 units, so they want the integral from 0 to 49. So the integral we're looking for is the integral from 0 to 49 of 11x to the negative 1/2 dx. So there. That's the setup of the problem. Make sure you copy that down so that when you go home you can do it. And it's 12:51. I held you a minute later than I should have, but folks, I'm not going to charge you for that. That was free.